how does the concavity of a curve describe rates of change? So how's the second derivative? We know that the second derivative measures how the first derivative changes. That's the rate of change of the first derivative. So the greater the magnitude of the concavity, now we haven't really worried about the number, we're just worried about whether it's positive or negative, so we knew it was concave up or concave down. But the number tells us the size of the concavity. So the greater the magnitude of the concavity, then the faster that rate of change is. That's a bigger number. So I've got something like this. There's P. What can I tell about the particle and what it's doing at P? Well, at that point, I know the first derivative is greater than 0. So I know it's increasing. The second derivative is less than 0. So the rate of change is decreasing because its derivative is negative. So that function is increasing at a decreasing rate. So it is getting, increasing, but it's getting slower and slower until eventually the rate of change will be 0. And it will then travel at a constant velocity. Its actual velocity is getting bigger and bigger, but the rate at which it's getting bigger and bigger is slowing down. It's acceleration, if you like. You're taking your foot off the accelerator. You're still moving forward. Okay, over here. Q then, once it gets to the other side, it's now decreasing, but it's still concave down. So this one is decreasing, but at an increasing rate because it's decreasing because it's negative, but its rate of change is slowing down. So it's decreasing, but at an increasing rate. I know that sounds weird, but if you look at the picture and think of the actual slope of the curve, what it's doing, and it's getting steeper and steeper. So whilst it is still decreasing, the slope of that graph is getting bigger and bigger. So its rate of change is growing. Okay, R then, it goes to the concave up section. It's still decreasing, but now it's changed to concave up. That one there is decreasing at a decreasing rate. So just imagine the tangent, what it's doing, and what the steepness is. As it moves down, it's still going down, but it's getting shallower. So its rate of change is getting smaller and smaller, decreasing at a decreasing rate. That brings us our final one there, when it's now on the other side. And now it's increasing again, but at an increasing rate. Now that we've got all 4 pictures there, it becomes a little bit easier. If you see the sign, just look at the sign. If the signs are in the same direction, then it's going to be happening at an increasing rate. You see how the first one up here at Q, they were both negative. So decreasing because it was negative, but at an increasing rate. At S, increasing at an increasing rate. See, they're both positive. When they were in opposite directions, one's positive, one's negative, then it's happening at a decreasing rate. So this one's increasing at a decreasing rate, this one's decreasing at a decreasing rate. That's really what you're looking at. Are the signs the same or are the signs different? Let's look at some practical questions now. This graph shows petrol consumption versus population. It just came out of a newspaper, we just clipped it out. That's a good graph, let's put it in the textbook. But that's what it's measuring. Now, at less than 20 people per hectare, people depend more on their cars for transport. Well, that makes sense. You're not going to have public transport if you've only got a few people in a very large area. What can be concluded about petrol consumption as population density increases? So this is the graph that's describing it. There's all the different towns. But really, we can look at this graph and consistently we can see that it's decreasing, but it's also concave up. So one's negative, one's positive. The signs are different. So it's decreasing at a decreasing rate. This one, also average annual temperature in Sydney. There's a blue graph and a red graph. How does the temperature change during autumn? Okay. At the start of autumn, by the way, the 2 different ones, it doesn't actually say there, does it? One's the minimum and one's the maximum for the day. At the start of autumn, and autumn of course starts in Ah, it's okay. Okay, so if we have a look at the curve in March, we can see that it would be decreasing at an increasing rate because the curve is concave down and the slope is negative. The signs are the same. So it's going to be at an increasing rate. However, during autumn, that rate slows down. And by the end of autumn, which is, so at the end of May or start of June, have a look at our graph, we can now see the concavity has changed at that point. So, yeah, the temperature's still going down, but at a decreasing rate. And now think about what's been happening in the past few months. Temperature starts going down, but it also, bang, it goes down real quick. But then as we move into winter, it's still going down, but just not as dramatic each day. Well, that's exactly what happens. Oh, this one I wrote a couple of years ago. It was kind of relevant at the time. On March the 22nd, the Prime Minister announced stage 1 shutdown restrictions in order to slow down the rate of new cases. I remember, those were the days. Here's a graph. I pulled out all the information and went, righto, let's get these graphs. Remember, we were obsessed with them at the time. We were as a maths teacher, it was a great time. It was a fantastic time. All of these graphs were being produced and things like that. Fantastic. So we had new cases and cumulative. Remember, they used to have press conferences and everyone would tune into the press conference. We had 1,000 more cases today and things like that. Oh, wow. Given that it takes about 5 to 6 days, and that's what they were saying at the time, it takes about 5 to 6 days for symptoms to show, do you think the measure has been effective? So that shutdown happened on the 22nd. Okay. Well, what happened 5 days later? 5 days later was the 27th of March. So on my graph, that's pretty much, we're getting towards the end of the graph there if you look at the scale. See, everyone was talking about the curve flattening. Do you remember that expression? They're saying we want the curve to flatten. Mathematicians were out there going, no, I want to see an inflection point. Because when the concavity changes, that's when the rate of change is changing. So that's what we were looking for. So 5 days later, the 27th of March, I think I can clearly see there has been an inflection point and the concavity of that curve has changed. Went from concave up to concave down. So that would suggest that even though the cases are increasing, it's now growing at a decreasing rate. That would seem to suggest, and as I said at the time, well, yes, it's very early, but it does appear that that measure was effective. And if you remember the first shutdown, it was very quick and it happened nicely. It did in that case work. Don't know we can say the same about the second one or not. That one we got a bit carried away with, didn't we? We went for ages on that one. Okay, 9, here we go.